Good morning everyone. I am Nandini Ghosh and now me along with my group members Jenifer, Hussain and Anikshit Kashyap will be presenting our final year project on the topic automated monitoring of sensor and fruit state using AI techniques as part of a greenhouse setup done under the guidance of Professor Kandarbo Kumar Sharma. So let's begin the presentation. This is the outline of our project. We will start with the introduction, then the literature review, then the motivation, next the problem formulation, and then the work methodology and approach under which there is the work done in phase 1 and phase 2, and then the conclusion, then limitations, and finally the future directions and the references. Introduction. Today, greenhouse is preferred in most places as a technique to create an ideal climatic conditions for plant growth. But the available manually monitored greenhouse systems require a direct human supervision and regular visits, causing distress to the farmers. It also decreases the yield due to the lack of proper regulation and monitoring. So, precise controlling and monitoring of greenhouse parameters, it is necessary to automate the greenhouse. Literature review. These are some of the papers we have gone through while making the proposed system. Motivation. We have chosen to work on this project keeping in mind the hardship faced by the farmers to keep a periodic check on greenhouse by making regular visits and failing which results in destruction of crop and the production rate. Problem formulation. Firstly, to design an Arduino-based greenhouse system for monitoring of greenhouse parameters, namely sunlight, carbon dioxide, soil moisture, temperature, and humidity. Secondly, to formulate a method for detecting the technical faults in the sensors used in the greenhouse system using logistic regression. And lastly, to design and train a CNN model for predicting the condition of fruit produced in the greenhouse, that is to predict whether the fruit is rotten or fresh. Now, the work methodology and approach. Work plan. Our work plan was, first of all, an Arduino-based system was developed for automated monitoring of greenhouse environment to increase the yield by providing an ideal climate for the plant growth inside the greenhouse. The sensors used to monitor the greenhouse might have some technical faults which would lead to inaccuracy in the received sensor output and in turn decrease the overall efficiency. So, to solve this issue, we have developed a technique using logistic regression to classify the sensors as defective or non-defective. This classification is done by analyzing the working threshold of the sensors. Again, to increase the yield and productivity of plants produced in the greenhouse, it is very important to harvest them at the right time. For this, we have designed a convolutional neural network and trained it using image datasets of various fruits. The model classifies the fruits as fresh or rotten based on the color, texture, size, etc. Work done in project phase 1. During the phase 1 of the project, we have designed an Arduino-based greenhouse system for the automated monitoring of greenhouse parameters, namely sunlight, soil moisture, carbon dioxide, temperature, and humidity. This is the block diagram of the system. Here, as you can see, the light, soil, carbon dioxide, temperature, and humidity sensors are connected to the input pins of the Arduino, and the Arduino, on the basis of the received data through the sensors, regulate the greenhouse parameters with the help of the actuators, that is light, fan, water pump, and heater, which are connected to the output pins. Working principle. The main component of our system is the Arduino microcontroller. The sensors used are light sensor, that is the LDR, temperature and humidity sensor, that is DHT11, soil moisture sensor, and carbon dioxide sensor, that is MQ135. The Arduino processes the data acquired through the sensors and accordingly changes the status of the actuators connected to its output pin. For the programming part, we have used the Arduino IDE and C language. For every greenhouse parameters, we have set a threshold value or a range of threshold values. While coding, the Arduino pins are first initialized and then pin modes, that is input or output, are declared. And if-else later is used by the Arduino microcontroller to compare the sensor outputs with the preset threshold value. Based on this comparison, the Arduino changes the status of the actuator. Flowcharts. So figure number 2 shows the flowchart of light intensity control. Here, when the light intensity of the greenhouse will be below the preset threshold value, then the light is turned on. Otherwise, the light is turned off. The experimental threshold that we have taken was 300. Now, figure 3 shows the flow chart for temperature control. When the temperature of the greenhouse is in the range of the threshold that we have set, then both the heater and the fan are turned off. When the temperature will be below the threshold, then the heater is turned on. And when the temperature will be above the threshold range, then the fan is turned on. The experimental threshold value that we have taken is in the range of 24 to 32 degrees Celsius. Figure 4 shows the flow chart of the soil moisture control. Here, when the moisture control of the soil will be in the range that we have set or above the range of the threshold, then the water pump is turned off, and when it is below the range of the threshold, then the water pump is turned on. Figure 5 shows the flow chart of carbon dioxide control. When the carbon dioxide content of the greenhouse is below the threshold set, then the fan is turned off, and when the carbon dioxide control of the greenhouse will be above the threshold value, then the circulating fan is turned on. The experimental value that we have taken for the carbon dioxide control was 400 ppm. Now, the next part will be presented by Jenifer Hussain.
In phase 2, we have applied artificial intelligence for automated monitoring of sensor faults and fruit condition in the Arduino-based greenhouse system. This is the working principle for detection of sensor faults. We have designed an Arduino-based greenhouse system that uses various sensors to monitor the environmental parameters like sunlight, carbon dioxide, soil moisture, temperature, and humidity. However, these sensors might have some technical issues that cannot be monitored manually. This would lead to inaccurate sensor outputs, which in turn would decrease the overall efficiency of the system. In order to solve this issue, we have formulated a method that can be used to classify the sensors as defective or non-defective using logistic regression. Logistic regression is a machine learning algorithm that predicts the probability of occurrence of the output given the information of the input. Logistic regression is mostly used as a binary event, that is, it will predict the output as either 0 or 1 for any value of the input. The output gets the value 1 if the event occurs, whereas it gets the value 0 if the event does not occur. In our case, we have used logistic regression for binary classification. So for that purpose, the model is trained such that it would give a binary outcome depending on the input. Every sensor has its own working threshold, and by analyzing the working threshold of every sensor, we have created the dataset. The output should be 1 if the sensor is in the working state, whereas the output should be 0 if the sensor is defective. This flowchart shows the workflow for classifying the sensors as defective or non-defective. The first step is to create the dataset. We have formed the dataset by considering the sensor data as the independent variable and the predicted output as the dependent variable. When we upload the code written in the Arduino IDE to the Arduino microcontroller, we get different sensor outputs depending on the variations in the greenhouse parameters. The values within the range of the sensor outputs is considered as the working threshold of the sensor. So for the independent variable, we have considered values which are within the range of working threshold, as well as values which are outside the range of the working threshold of the sensors. For values within the range, the corresponding dependent variable value is set to 1, and for values outside the range, the corresponding dependent variable value is set to 0. The next step is to pre-process the data and apply machine learning. In the pre-processing step, we have imported the Python libraries that are to be used in our program. We have used pandas and matplotlib libraries. Then we have imported the dataset by reading the CSV file to data frame format. Following this, we have extracted the independent and dependent variables from the dataset and stored them in variables x and y respectively. In case of logistic regression, the independent variable is predefined to be a 2D array, while the dependent variable should be a 1D array. Hence, we have converted the independent variable to a 2D array. The next step is to apply the logistic regression algorithm and train the model. We have imported the logistic regression class of the sklearn library. After importing the class, we have created a classifier object and used it to fit the model to logistic regression. The model.fit function is used for this purpose, and the independent and dependent variables are given as arguments to this function. With this, we have completed the training of our model using the dataset. The final step is to predict the result and test the accuracy of the model. The results are predicted using the model.predict function that takes the testing data as the argument. We have trained the model with values that are within the working threshold of the sensor, as well as values that are outside the range of the working threshold. So in order to check if the model is predicting the accurate output, we have given some random values as testing data. For values within the range, the predicted output is 1, whereas for values outside the range, the predicted output is 0. For testing the accuracy, we have used model.score function that takes the dependent and independent variables as the arguments. The same logic is implemented to detect technical faults in all the 4 types of sensors used in the greenhouse system. Only the datasets are created separately due to difference in their working thresholds. In the following slides, we have shown the experimental results for all the 4 sensors. The results are similar since the logic is same. We have determined that the working threshold of LDR is in the range of 1 to 470. In figure 7, we can see that when we give the input as 70, the predicted output is 1, and a message is thrown showing that the sensor is working. However, when we set the input to be 800, we get the predicted output as 0, and a message is shown stating that the sensor is not working. The accuracy is found to be 75%. Figure 8 shows the scatter plot. It is used to observe the relation between the input and the predicted output. In the x-axis, we have the set of values for the input, and in the y-axis, we have the predicted output corresponding to each input. Similarly, in figure 9, we have plotted a graph showing the relationship between the input and the predicted outputs. We have similar results for the temperature and humidity sensor, soil moisture sensor, and finally the carbon dioxide sensor. The rest of the slides will be presented by Anikshit and Kashyap.
Working principle for prediction of fruit condition. In a greenhouse, checking the condition or the state of the fruit is very important, as it tells us which fruits are ready to be plucked and which are getting rotten. It has 2 main benefits. It prevents human error, and secondly, it predicts the right time to harvest the fruits. We have formulated a method using convolution neural network to determine which fruits are being fresh and which are being rotten. For prediction of fruit condition, we have designed a CNN model. So what is CNN? CNN stands for convolution neural network. It is a type of feed-forward neural network. CNN is a class of artificial neural network which is used for image recognition and processing. So for this purpose, we have separated 2 datasets, the fresh and the rotten fruit dataset. Basically, the system checks the color of the fruits in determining the fruit condition. Fruits with dark patches are indicated as rotten, whereas bright colored fruits with no dark patches are indicated as fresh. So this is the flowchart for our CNN model. So in order to design that, first we have downloaded a dataset which consisted of fresh and rotten fruit images. These datasets have fruits of a certain type. So then we separated this dataset into 2 categories, the test and the trained dataset. In the test dataset, we used nearly 400 to 500 images of both the rotten and fresh fruits of a certain type. Similarly, we used approximately 1800 to 2000 images of the rotten and fresh fruits in the trained dataset of a certain type of fruit. Then this data is pre-processed. The CNN model is designed using Keras and TensorFlow. We have imported sequential as our neural network is a sequential neural network. We have imported con 2D as because all the images are basically 2D. We have imported max pooling. It is used to calculate the highest values in each patch. The results are basically downsampled. We have imported flatten. It converts the resultant 2D arrays into a single long continuous linear vector. Lastly, we have imported dense. It is used to fully connect the neural network. This is how we developed the CNN model, and how the images were reshaped and resized. Then we have set optimizers and activation functions. For optimizers, we have used Adams, and for activation function, we have used ReLU and Sigmoid. Then lastly, the test code is run to check whether it predicts the conditions of the fruit correctly. Experiment result for fresh fruit. As you can see, this is a banana picture, so we can clearly say that it is a fresh banana by looking at the color of the banana. So our system also predicted it correctly by giving the output as fresh. This is the experimental result for rotten fruit, and here you can see the banana has been rotten. It is completely black, and the system predicted it correctly by giving the output as rotten. In both of our cases, we have an accuracy of about 98%, as you can see this output below. So this is the video of the live working model of the system that we have created.
As you can see, here the LDRs are not illuminated, so the lights are turned on. Once the LDRs gets illuminated, the lights start to turn off according to the amount of the intensity of the light falling on the LDRs. Here, we can see the temperature is in between the threshold temperature that we have set. So, neither the heater or the cooler is turned on. Suppose I set the temperature below the minimum threshold temperature. Then the heater gets turned on, which is indicated by the red LED. And if I set the temperature above the maximum threshold temperature, then the cooler gets turned on, indicated by this blue LED. Here, we can see the soil has perfect moisture present in it. It is between the minimum and maximum threshold that we have set. The green LED is indicating that the soil moisture is balanced. If I set the soil moisture below the minimum threshold value, then the water pump gets turned on, indicated by this blue LED. If I set the soil moisture above the maximum threshold value, then the water pump does not turn on. This yellow LED indicates that the soil is extremely wet. We have tested different values of the sensors to see whether our system predicts correctly. Once our program is executed, we can see it is predicting correctly for each and every value of the sensor. As you can see, we have taken this picture of a fresh banana. When we test this picture, our system is predicting it correctly by giving the output as fresh. Now, you can see this banana is rotten. When we test this picture, the system is predicting it correctly by giving out the output as rotten. In both of our cases, the accuracy of the model is about 98%.
So the conclusion is that our system automatically checks and maintains the greenhouse parameters as required by the user. So it can detect whether the sensors are working fine or has it gone damaged. So it increases the overall yield and productivity of the system. So the limitations are that the system does not provide the user with remote monitoring of the greenhouse parameters. Since we have not used any actuators in our system, so it cannot control the variations in the greenhouse parameters. So detecting the sensor fault has low accuracy because we have used less number of threshold values in the dataset. The CNN model designed to predict the fruit condition cannot detect the reason due to which the fruit has gone rotten. For future direction, we can design an Android app to remotely monitor and control the greenhouse parameters. SMS alerts can be sent to the user if some sensors or actuators are found to be damaged. Actuators can be added to the full working system. Sensor fault accuracy can be increased by adding more threshold values to the dataset. Fruit disease detection can be added to the system. Wireless technology can be implemented in the system in order to be more reliable and cost effective for the larger areas. This is the Gantt chart of our project. These are the references that we have taken. Anikshit, Kashyap.
Nandini, Ghosh.
Jenifer, Hussain.
Thank you.
Thank you.
Thank you.